All right, let's dive right in. Organic chemistry is just everywhere. It's in the plastics in our phones, the medicines we take, pretty much everything. And that means there are literally billions of different carbon compounds out there. So the big question is, how on earth do you even begin to keep track of them all? I mean, it really sounds impossible, doesn't it? Think about it. Every single one of those billions of molecules needs a unique name, a name that tells you exactly what it is. You'd think you'd either run out of names or the system would be so ridiculously complicated that no one could ever figure it out.
But, well, chemists came up with a really elegant solution to this whole mess. It's called the IUPAC system. Now, that's a mouthful. It stands for the International Union of Pure and Applied Chemistry. The key thing is, before this system, things were chaotic. Chemists used all sorts of common names. Is it wood alcohol, grain alcohol? Who knows? It was confusing. So IUPAC created a universal language. The idea was that any chemist anywhere on the planet could see a name and know exactly what the molecule looks like, with zero confusion. So let's start learning this language.
Okay, so just like learning any new language, you got to start with the basics, right? The alphabet, the simple words. In this chemical language, our words describe the length of the carbon chain. This is the backbone of pretty much every organic molecule we're going to talk about.
And here's the best part. This foundation is actually super simple. This table you're looking at, that's basically our chemical alphabet. If there's one carbon, the root is meth. 2 carbons, F. 3 is prop, and so on. You see pent for 5, hex for 6. It's just a straightforward code for counting carbons. Easy enough, right? Okay, ready for our first grammar rule? It's a piece of cake. If you've just got a simple, straight chain of carbons, all connected by single bonds, you just slap the suffix -ane on the end. So remember our 5-carbon root, pent? Well, that just becomes pentane. See? Simple as that.
All right, but let's be real. Molecules aren't always just nice, neat, straight lines. A lot of them have little branches sticking off the sides. I like to think of these branches as adjectives. They add a bit of descriptive flair to our main noun, that carbon backbone. So, how in the world do we name those?
Well, there are 2 golden rules for this, and they're super important. First thing you do, find the longest possible chain of carbons that you can trace without lifting your finger. That's your main chain. Then, rule number 2, you've got to number the carbons in that chain. And here's the trick. You have to number them so that the branch gets the lowest possible number. Think of it like a street address. You want to give that branch the lowest, simplest address you can.
Okay, let's put this into practice. Take a look at this molecule here. We can see the longest chain is 5 carbons long, and it's got one little branch sticking off it. So to give that branch its lowest possible address, should we start counting the carbons from the left side, or should we start from the right?
Let's actually walk through it. If we count from left to right, the branch ends up on carbon number 4. Okay, now let's try it the other way. If we count from right to left, that same branch is on carbon number 2. And since 2 is obviously lower than 4, starting from the right is the winner. That's the correct way to do it.
So now we have all the pieces of our puzzle. First, the branch. It only has 1 carbon, so its root is meth. When it's a branch, we call it a methyl group. We already figured out its address is on carbon number 2. And we know the main chain, with 5 carbons, is pentane.
And now we just stick them all together in the right order. Address first, then the branch, then the main chain. So we get 2-methylpentane. And boom, there it is. See how that's not just some random name? It's a perfect blueprint. It gives you the exact instructions to build that molecule from the ground up.
Okay, so we've got the basic structure down. But what about the interesting stuff? What gives a molecule its actual personality? What makes an alcohol? Or what gives vinegar that sour kick? Well, that all comes down to something called functional groups. They're literally the personality of the molecule.
So what exactly is a functional group? It's really just a special group of atoms that latches onto a carbon chain. And once it's there, it completely takes over. It determines the molecule's properties, how it's going to react with other things. Basically, it defines what that molecule does.
Let's check out a couple of these personalities. If you spot an OH group attached, congrats, you've got an alcohol, and the name gets a new ending, ol. So our simple 2-carbon ethane suddenly becomes ethanol. Yep, that's the alcohol in alcoholic drinks. Or how about a COOH group? That makes it a carboxylic acid. So ethane becomes ethanoic acid, which you probably know better as vinegar. See, that little group changes everything.
This brings us to one last and honestly pretty mind-bending idea. What happens if you take the exact same set of atoms, but you just connect them in a different order?
This is where the precision of this chemical language becomes absolutely fundamentally crucial.
This idea has a name. It's called isomerism. And isomers are amazing. They are compounds that have the exact same molecular formula, the same shopping list of atoms, if you will, but they're built differently. It's like having the same Lego bricks but building two totally different things. And because their structure is different, their properties are completely different too.
Okay, just look at this example. Both of these molecules have the exact same formula, C3H8O, same parts list, but look closely. On the left, that OH group is hanging off the first carbon. That makes it propane-1-ol. On the right, the OH group has moved to this second carbon. Now it's propane-2-ol, which you probably know as rubbing alcohol. Same atoms, totally different molecules, totally different names. This is why those numbers are so important.
So when you step back and look at it, what have we really learned? This whole IUPAC thing, it's so much more than just a stuffy set of rules. It's a language where every single name is a detailed blueprint. It gives you the exact instructions to build a molecule, piece by piece. It's just an incredibly powerful and honestly beautiful system for making sense of a gigantic and chaotic chemical universe.
And it kind of makes you wonder, doesn't it? We've got this system, this language, that lets us decode billions of different compounds using just a handful of simple rules. So the question is, what other elegant systems are out there, hiding in plain sight, just waiting for us to figure out their language?